Welcome! In this video, we will be exploring LeetCode problem number 1361, titled Validate Binary Tree Nodes. This problem challenges us to verify if a given set of nodes forms a valid binary tree based on specific constraints. We'll break down the problem, analyze the requirements, and discuss effective approaches to solve it. Let's dive in. In this problem, we are tasked with determining whether a set of node relationships forms a valid binary tree. You are given n nodes, labeled from 0 to n1, and two arrays, left child and right child. For each node I, left child, I, tells us the left child of that node, and right child, I, tells us the right child. If either value is -1, it means that node I does not have a child on that side. A binary tree is considered valid if it satisfies three important conditions. First, there must be exactly one root node, which is a node with no parent. Second, every other node must have exactly one parent. Finally, all n nodes must be part of the tree, meaning there cannot be any disconnected nodes. Your goal is to write a function that determines whether the given relationships meet these criteria. Now, let's look at the parameters and expected output of the function. The input includes three parameters: n, which is the number of nodes labeled from 0 to n1, left child, an array where each element represents the left child of a node or -1 if there is no left child, and right child, which similarly represents the right child of each node or -1 if there is no right child. The function should return a Boolean value, true if the relationships form a valid binary tree, and false otherwise. For example, consider the input where n equals 4, left child equals 1, -1, 3, -1, and right child equals 2, -1, -1, -1. These inputs describe relationships between nodes that we will analyze next. The output for the given input is true, meaning the relationships form a valid binary tree. Here's why. The tree structure can be visualized as follows: node 0 has a left child 1 and a right child 2. Node 2 has a left child 3. Nodes 1 and 3 do not have any children. This structure satisfies all the conditions for a valid binary tree. Node 0 is the root since it has no parent. Every other node has exactly one parent, and all nodes are connected, forming a single tree. This example demonstrates how the relationships align with the given definition of a valid binary tree. In another example, however, the relationships do not form a valid binary tree. Consider the input where n equals 4, left child equals 1, -1, 3, -1, and right child equals 2, 3, -1, -1. The output in this case is false. The issue lies with node 3, which has two parents, node 2 and node 1. This violates the condition that every node other than the root must have exactly one parent. As a result, the relationships fail to meet the criteria for a valid binary tree, and the function correctly returns false. Here's another example where the relationships are invalid due to a cycle. When n equals 2, left child equals 1, 0, and right child equals -1, -1, the output is false. In this case, there is a cycle between nodes 0 and 1. Specifically, node 0 is the parent of node 1, and node 1 is the parent of node 0. Cycles are not allowed in a binary tree, as they break the requirement for a single root and a hierarchical structure. Therefore, this input does not represent a valid binary tree. Finally, let's discuss some edge cases and constraints. For example, if there is only one node with no children, such as n equals 1, left child equals -1, and right child equals -1, the output is true because this represents a valid tree with just one root node. On the other hand, if there are disconnected nodes, such as n equals 4 with left child equals -1, -1, -1, -1, and right child equals -1, -1, -1, -1, the output is false because the nodes are not connected into a single tree. Another edge case is when there are multiple roots, such as n equals 3, left child equals -1, 0, -1, and right child equals -1, -1, -1. Here, both node 1 and node 2 function as root nodes, which is not allowed. These cases highlight the importance of checking all conditions for a valid binary tree. To solve the problem of validating binary tree nodes, we need to ensure that the given n nodes form a valid binary tree according to three key conditions. First, there must be exactly one root node, which is a node with no parent. Second, all nodes need to be connected, meaning the tree cannot have any disconnected components. Third, there should be no cycles, so each node should have at most one parent. One approach we considered was the brute force method. The intuition behind this was to manually check the tree properties by carefully tracking parent-child relationships. The steps involved counting incoming edges for each node to find the root, traversing all nodes to confirm connectivity, and using a visited set to detect cycles. However, this approach has a major drawback: its time complexity is O(n) squared, as verifying parent-child relationships for all nodes results in nested traversals. This makes it inefficient for large inputs, and the manual checks increase the complexity of implementation. A more efficient approach is to use graph traversal techniques to validate the binary tree. The intuition here is to represent the tree as a directed graph and perform a top-down traversal like DFS or BFS to ensure all the necessary properties. The process starts by counting the incoming edges to identify the root node. If there's no root or more than one root, it's immediately invalid. Then, we traverse the graph using DFS or BFS to confirm that all nodes are connected and that there are no cycles. To do this, we track visited nodes during traversal. Finally, we ensure that all n nodes are visited exactly once, validating the structure completely. This approach has a time complexity of O(n), as each node is processed only once during traversal. The benefits are clear: linear time complexity makes it highly efficient, and leveraging graph traversal methods ensures correctness while reducing redundancy. The optimized graph traversal approach was ultimately chosen because it balances efficiency and clarity. Unlike the brute force method, it avoids redundant manual checks and directly applies graph theory principles to validate the binary tree. Counting incoming edges is a quick way to identify the root node, and performing a single DFS or BFS traversal ensures there are no cycles or disconnected components. This makes the solution both scalable and elegant. A key insight here is that a valid binary tree must have exactly one root, which can be easily determined by analyzing the incoming edges. Additionally, graph traversal techniques like DFS or BFS are naturally suited for detecting cycles and verifying connectivity. While the brute force approach may seem simpler conceptually, it becomes impractical for larger datasets due to inefficiencies. The graph-based strategy, with its linear time complexity, is the ideal choice for solving this problem, as it ensures correctness without sacrificing performance or clarity. To determine if the given nodes form a valid binary tree, we need to follow a structured approach. A binary tree has three critical properties: it must have exactly one root, it must be fully connected, and it must be acyclic. To begin, the first step is counting parent references. We initialize an array called parentCount where each element starts at 0. This array keeps track of how many times each node appears as a child. We achieve this by traversing the left child and right child arrays. Every time a node is referenced as a child, we increment its count in the parentCount array. For example, if a node I has a valid left child, we increment the count for left child, I. Similarly, if it has a right child, we increment the count for right child, I. This step is crucial because a valid binary tree requires exactly one root node, which is the only node with no parent, and all other nodes must have exactly one parent. Counting these references lays the groundwork for identifying structural validity. Now that we have the parent counts, the next step is to identify the root node. A root is a node with a parent count of 0, meaning no other node references it as a child. We count how many nodes satisfy this condition. If there is no such node, or if there is more than one, the structure cannot form a valid binary tree, and we return false. If there is exactly one root, we record it and move forward. Once the root is identified, we need to verify connectivity and acyclicity. To do this, we use either a breadth-first search, BFS, or depth-first search, DFS, starting from the root. During this traversal, we maintain a visited set to track all nodes that we visit. For each node, we mark it as visited and traverse its children, but if we encounter a child that has already been visited, this indicates a cycle, and we return false. After completing the traversal, we check if all n nodes were visited. If any node remains unvisited, it means the graph is disconnected, and we return false. This ensures that the graph is fully connected and free of cycles, fulfilling two fundamental properties of a binary tree. With these steps in mind, let's highlight the key insights that underpin this algorithm. First, counting parent references ensures that each node has at most one parent, and it allows us to identify the root node. This is critical because a valid binary tree must have exactly one root. Next, the connectivity check ensures that all nodes are reachable from the root, confirming there are no disconnected components in the graph. Finally, the cycle detection ensures that the graph is acyclic, which is a fundamental property of trees. To implement this efficiently, we use three main data structures. The parent count array helps validate parent-child relationships and uses O(n) space. The visited set tracks nodes during traversal, ensuring connectivity and acyclicity, also using O(n) space. Finally, a queue or stack facilitates the BFS or DFS traversal, which is efficient and requires O(n) space as well. In terms of complexity, the algorithm runs in O(n) time. Counting parent references is linear, and the traversal also takes linear time. The overall space complexity is O(n) due to the storage used by parent count, visited, and the traversal data structures. When applying this algorithm, it's important to account for edge cases that might arise. One such case is a disconnected graph, where not all nodes are reachable from the root. For example, if n equals 3, left child equals 1, -1, -1, and right child equals -1, 2, -1, nodes 2 and 3 are disconnected, so the result is false. Another case is when the graph contains a cycle. For instance, if n equals 3, left child equals 1, -1, 1, and right child equals -1, -1, -1, there's a cycle involving node 1, so the result is false. A third case involves multiple roots. If n equals 3 and both left child and right child are arrays of -1, all nodes are roots, violating the single root property, and the result is false. Lastly, consider a valid binary tree, such as n equals 2, left child equals 1, -1, and right child equals -1, -1. Here, the structure satisfies all conditions, so the result is true. By addressing these edge cases, we ensure the algorithm handles all potential scenarios effectively. Here, we start by defining a class called solution and implementing the function validate binary tree nodes. The function takes three parameters, the number of nodes n, and two lists, left child and right child, which represent the left and right children of each node in the tree. To validate the binary tree, the first step is to ensure that there is exactly one root. We initialize a parent_count array of size n with all values set to 0. This array will help us keep track of how many times each node is assigned as a child. Then, we iterate through all the nodes. For each node, if it has a left child, we increment the parent count for that child. Similarly, if it has a right child, we increment the parent count for that child as well. Once this loop completes, we identify the root candidates, nodes with a parent count of 0. A valid binary tree must have exactly one root, so if the number of root candidates is not equal to 1, we return false. If there is exactly one root, we proceed with the validation process by storing the root node. The next step is to ensure that the tree is fully connected and acyclic. To do this, we use a breadth-first search, or BFS. We initialize a visited set to track the nodes we've already processed, and we create a queue starting with the root node. While there are nodes in the queue, we pop one out to process it. If this node has already been visited, it means there is a cycle in the tree, so we immediately return false. Now, as part of the BFS process, we add the current node to the visited set to mark it as processed. If the current node has a left child, we append that child to the queue. Similarly, if it has a right child, we append the right child to the queue. This ensures that all children of the current node are processed in subsequent iterations. The BFS loop continues until the queue is empty, which means all reachable nodes have been visited. Finally, we validate whether the tree is correctly structured by checking if the number of visited nodes is equal to n. A valid binary tree must visit all nodes exactly once, and if this condition is met, we return true. Otherwise, we return false, as it indicates the tree is either disconnected or contains extra nodes. This implementation efficiently ensures that the binary tree adheres to the required conditions of having a single root, being fully connected, and being acyclic. Here, we start by checking if the binary tree has exactly one root. To do this, we initialize an array called parentCount to keep track of how many times each node is referenced as a child. We then iterate through all the nodes. For the left and right children of each node, if they exist, that is, if they're not equal to -1, we increment their corresponding count in the parent count array. After this, we look for nodes that are never referenced as children by iterating through the parent count array. These nodes are considered root candidates since they have no parent. Finally, we check if there's exactly one root candidate. If there are none or more than one, we immediately return false, as this violates the binary tree property. If we have exactly one root, we proceed to verify that the tree is fully connected and contains no cycles. Using a breadth-first search, or BFS, we start by initializing a queue with the root node and a set called visited to track nodes we've already processed. While the queue is not empty, we dequeue a node and check if it's already in the visited set. If it is, this means we've encountered a cycle, and we return false. Otherwise, we add the node to the visited set. Then, we enqueue the left and right children of the current node, if they exist. This ensures all reachable nodes are explored systematically. The BFS traversal helps identify if the graph is connected and acyclic, which are essential properties of a valid binary tree. Finally, after the BFS traversal is complete, we check if the number of visited nodes matches the total number of nodes, n. If they are equal, it means every node was visited exactly once, confirming that the tree is fully connected and contains no disconnected components. If not, it indicates that some nodes are unreachable from the root, and we return false. By combining these checks, we ensure the structure adheres to all the properties of a valid binary tree. The function then returns the result of this final condition. To validate whether the given nodes form a valid binary tree, we start by calculating the parent counts for each node. Initially, we set up an array called parent_count with all zeros, one entry for each node. Then, we process the left child array. For node 0, the left child is 1, so we increment the parent count for node 1, making it 1. Similarly, for node 2, the left child is 3, so we increment the parent count for node 3. At this point, the parent_count array becomes 0, 1, 0, 1. Moving on to the right child array, node 0 has a right child of 2, so we increment the parent count for node 2. This gives us the final parent_count array of 0, 1, 1, 1, where each index represents the number of times that node appears as a child. Next, we identify root candidates. A root is a node that doesn't have any parent, meaning its parent count is 0. Here, only node 0 has a parent count of 0, so our root candidate is 0. With exactly one root candidate found, we identify node 0 as the root. Now, we need to ensure the tree is connected and contains no cycles. For this, we perform a breadth-first search, BFS, starting from the root. We initialize an empty set called visited to track visited nodes and a queue containing the root, which is 0. Starting with node 0, we mark it as visited and add its children, nodes 1 and 2, to the queue. The queue becomes 1, 2. Next, we process node 1, mark it as visited, and move on since it has no children. Then, we process node 2, mark it as visited, and add its child, node 3, to the queue. The queue now contains 3. Finally, we process node 3, mark it as visited, and complete the BFS since there are no more nodes to process. At the end, all nodes have been visited, and the length of the visited set matches n, confirming the tree is connected and acyclic. Since all criteria are met, the output is true. Now, let's analyze an example where the input does not form a valid binary tree due to multiple roots. We begin by calculating the parent counts. Starting with left child, node 0 has a left child of 1, so we increment the parent count for node 1. Similarly, node 2 has a left child of 3, so we increment the parent count for node 3. At this point, the parent_count array is 0, 1, 0, 1. Next, we process the right child array. Node 0 has a right child of 2, so we increment the parent count for node 2. Finally, node 3 has a right child of 0, so we increment the parent count for node 0. Now, the parent_count array is 1, 1, 1, 1. Every node has a parent count greater than 0, meaning there are no nodes without parents. Consequently, there are no root candidates, which violates the requirement of having exactly one root. This confirms that the tree is invalid, and the output is false. In the next example, we analyze an invalid binary tree where a cycle exists. We start again with the parent count calculation. For the left child array, node 0 has a left child of 1, so we increment the parent count for node 1. Similarly, node 2 has a left child of 3, so we increment the parent count for node 3. Additionally, node 3 has a left child of 0, so we increment the parent count for node 0. At this point, the parent underscore count array is 1, 1, 0, 1. Next, we process the right child array. Node 0 has a right child of 2, so we increment the parent count for node 2. The final parent underscore count array becomes 1, 1, 1, 1. Every node has a parent count greater than 0, meaning no node qualifies as a root. Without a root, the tree cannot be valid. Since there are no root candidates, we can already conclude that the tree is invalid. However, let's consider the potential presence of a cycle. If we attempted to perform a BFS, we would eventually revisit a previously visited node due to the cyclic reference between nodes 0 and 3. This confirms the presence of a cycle, which further invalidates the tree. Combining these observations, we conclude that the tree is not a valid binary tree, and the final output is false. To analyze the time complexity of our solution, we break it down into three main operations. First, we calculate the parent count for each node. This involves iterating through all n nodes and updating the parent underscore count array for the left and right children of each node. Since these are constant time operations performed for every node, this step has a time complexity of O(n). Next, we identify the root candidates by iterating through the parent underscore count array, which also contains n elements, resulting in another O(n) operation. Finally, we execute a breadth-first search, or BFS, starting from the root node. In this process, we visit each node exactly once and process its children, which amounts to O(n) operations. Therefore, each of these steps contributes linearly to the overall time complexity. Now, summing up the time complexity of all three steps, we have O(n) for parent count calculation, O(n) for root candidate identification, and O(n) for BFS traversal. These sequential operations lead to an overall time complexity of O(n) plus O(n) plus O(n), which simplifies to O(n). Moving on to space complexity, the parent underscore count array is the first contributor. Since it stores one integer for each of the n nodes, it requires O(n) space. The visited set is another important component, as it keeps track of nodes visited during BFS. In the worst case, this set grows to include all n nodes, contributing another O(n) to the space complexity. Lastly, the BFS queue temporarily stores nodes to be processed. While the queue size fluctuates during traversal, in the worst case for a general tree, it can hold up to all nodes in the bottommost level of a complete binary tree, which is also O(n). Adding these space requirements together, we see that the parent underscore count array, visited set, and BFS queue each contribute O(n) to the total auxiliary space usage. Thus, the overall space complexity remains O(n). Comparing this to a brute force approach, which might involve checking all pairs of nodes for connectivity or cycles, the naive method could result in O(n squared, or worse due to excessive redundant operations. However, the optimized approach outlined here avoids such inefficiencies. By performing a linear pass to calculate parent counts, identify the root, and validate the tree structure using BFS, we achieve a time complexity of O(n). This efficiency is rooted in the fact that each node is processed at most once, making this approach the most optimal for the problem. Now, let's examine the best, average, and worst-case scenarios for this algorithm. In the best case, the input is already a valid binary tree, allowing BFS to visit nodes sequentially without unnecessary checks. Time and space complexity remain O(n). In the average case, we process a general tree structure without any additional optimizations, but the complexity still remains O(n). Even in the worst case, where the tree-like structure requires BFS to visit all nodes, the complexity does not exceed O(n), as each node is processed exactly once. Mathematically, the big O proof stems from the fact that the algorithm performs a constant number of operations per node and edge, and since the input size is proportional to n, the dominant term is linear. This ensures that both time and space complexity scale linearly with the number of nodes, making the solution efficient and well-suited for large inputs. When working on this problem, there are several common mistakes to be mindful of. First, ensure that you check for exactly one root node in the tree. This is critical because a valid binary tree must have a single root, and failing to verify this can lead to errors, especially in cases where there are multiple disconnected components. Multiple roots indicate that the graph is not a single tree, which violates the definition of a binary tree. Next, always check for cycles in the graph. A binary tree, by definition, cannot contain cycles, and neglecting to detect them can result in incorrect solutions. Cycles mean that nodes are revisited, which is not possible in a tree structure. Another mistake to avoid is overlooking unused nodes. The problem guarantees n nodes, and all of them must be part of the binary tree. Failing to account for unused nodes implies that the graph is incomplete, which again violates the binary tree definition. Lastly, handle edge cases carefully. For example, a single node tree or an empty tree are valid scenarios. Some solutions incorrectly assume that n is always greater than or equal to 2, leading to failures in these special cases. Addressing these mistakes will help ensure a more robust solution. Mismanaging parent-child relationships is another common issue. For example, a parent may end up with two identical children, which is invalid in a binary tree. Each parent must have at most two distinct children, so handling the child-parent mapping correctly is crucial to avoid logical errors. Now, when preparing for interviews, it's helpful to think of this problem in terms of graph properties. A binary tree is essentially a graph that is acyclic, connected, and has exactly one root. Understanding these properties will guide you in crafting a correct solution. Interviewers may also pose follow-up questions, such as how your approach would handle cases where there aren't exactly n nodes in the input, or how it would adapt if the graph were undirected instead of directed. Additionally, while DFS and BFS are popular techniques for solving this problem, using a union-find data structure can simplify the process of detecting cycles and verifying connectivity. However, union-find may feel less intuitive if you're new to it. Lastly, always aim for a solution with O(n) time complexity. Since the problem guarantees that n is at most 10,000, efficient linear approaches are both feasible and expected. This problem is closely related to several others on LeetCode, and practicing them can help solidify your understanding of the concepts involved. For instance, problem 261, graph valid tree, involves a very similar task of verifying whether a given graph is a valid tree. Another example is problem 323, number of connected components in an undirected graph, which focuses on counting connected components and is helpful for understanding graph connectivity. Then there is problem 684, redundant connection, which deals with detecting and removing cycles in a graph, an important skill for ensuring that a binary tree remains acyclic. Lastly, problem 207, course schedule, involves checking for acyclicity in a directed graph using topological sorting. While this problem revolves around scheduling tasks, the underlying technique has parallels to cycle detection in this problem. Exploring these related problems can expand your toolkit and deepen your grasp of graph-related challenges. There are several approaches you can use to solve this problem, each with its own trade-offs. A straightforward method is to use DFS or BFS traversal to verify connectivity and detect cycles. By maintaining a visited set, you can track which nodes have been explored. This approach is intuitive and relatively easy to implement, but it requires additional steps to ensure that all nodes are counted and that there is exactly one root. Another option is to use the union-find data structure, also known as disjoint set. This method is highly efficient, especially when enhanced with path compression and union by rank. It simplifies the process of detecting cycles and verifying connectivity but may be less intuitive if you're unfamiliar with the technique. Finally, you could use an in-degree count to verify the single root condition and validate parent-child relationships. This approach is simple and effective for ensuring that there's only one root, but it doesn't inherently check for cycles, so you'd need to combine it with additional traversal for full validation. Each of these methods has its strengths and weaknesses, so the best choice depends on your familiarity with the techniques and the specific requirements of the problem. Great work! In summary, we tackled the problem of validating binary tree nodes by applying graph traversal techniques and verifying key properties of binary trees. Remember the importance of understanding tree structures and their constraints to solve similar problems. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!